Hello guys, welcome to my channel, and in this video I'll explain you article number 2.8.3 potential energy of a dipole in an external field. In my previous video I explained you that what will be the potential energy for charge placed in an electric field. Then we have seen a system of charges placed in an electric field, their potential energy. Okay, so now we'll see a dipole. When a dipole is placed in an electric field, what will be the potential energy of the dipole? Okay, so we'll start. Consider a dipole with charges q1 plus q and q2 is equal to minus q placed in an uniform electric field. Okay, so this is a uniform electric field represented by parallel lines. Okay, and this is a dipole minus q plus q. Okay, you know what a dipole is: equal and opposite charges separated by distance. So dipole, it is placed in an electric field. As seen in the last chapter, in a uniform electric field, the dipole experiences no net force but experience a torque tau given by. Okay, so in our first chapter we have seen that when a dipole is placed in an electric field, so it will experience no net force because this charge will experience a force in this direction given by F is equal to QE. Okay, and this charge will experience the force in the opposite direction of electric field, because these are the equal and opposite forces acting on the same body but in different direction. Net force will be zero, but a torque will be acted. Okay, rotational force will be acted, and the electric field will try to rotate the dipole with the alignment with the electric field. Okay, so our torque will be acted on the dipole. Yeah, so the given the formula or the equation of the torque will be P times E, where P is the dipole moment and E is the electric field. This we have studied in the previous chapter. Okay, which will tend to rotate it unless P is parallel or anti-parallel. Okay, it will try to rotate it, making it align with the electric field. Okay, suppose an external torque torque external is applied in such a manner that it just neutralizes this torque and rotates in the plane of paper from theta naught to theta 1 at an infinitesimal angular speed and without angular acceleration. So the electric field is applying a torque on this dipole and it is trying to rotate the dipole with the alignment of the electric field. Suppose we apply an external torque opposite to this torque applied by the electric field, okay, which will rotate it on the opposite direction. Okay, so what will be the work done by this torque? Okay, suppose, and this torque will act in such a way that the angular speed with which we rotate the dipole will be very small. Okay, so angular speed value infinitesimal angular speed. Okay, so that there is no angular acceleration. This is similar to discussion that we discussed when we bring a charge from infinite in the opposite to the electrostatic field, and there also we exert a force or external force such that the net force is zero. Okay, and there is no acceleration on the charge. So this is a similar concept here. So we are applying a torque, external torque, which is opposite to this torque. Okay, and which will the angular speed will be very small, so that there is no angular acceleration. Now the small work done by the torque in moving the dipole through a small angle d theta will be dw is equal to tau d theta. Okay, and for angle theta 1 to theta 2 will just integrate it to those limits. Okay, so total work done in rotating the dipole through angle of theta naught to theta 1, okay, that would be what, just integrated. Okay, so this is torque external d theta. Okay, we'll integrate from the limit to the limit d theta naught to theta 1. Okay, now we'll put the value of t external, torque external, because it is equal to the value of the torque exerted by the electric field, and the torque exerted by the electric field on dipole was P sine theta. So this will be also equal, because we have said that we are applying an equal and opposite torque. Okay, so P sine theta, this is the value of torque. Okay, now we'll just integrate. P is a constant, dipole moment is a constant, electric field is uniform. We'll take this both out of the integration and we'll integrate sine theta, and you know the integration of sine theta is minus cos theta. When we put minus cos theta and we'll put the limit, so this will be cos theta 1 and this theta naught. So what we'll get? We'll get minus cos theta 1 plus cos theta naught, and we can rearrange them and write it like this. Okay, so this is the work done by the external torque in moving the dipole, rotating a dipole through theta naught to theta 1. Okay, this work is stored in as the potential energy of the system, and this work is obviously stored as the potential of the system. We can then associate potential energy u theta with an inclination of the dipole. Similarly to other potential energies, there is a freedom choosing the angle where the potential energy u is taken as 0. Okay, so we'll choose a particular angle for which the potential energy is 0, because the difference of potential energy, that is significant. So we'll choose one particular angle as 0 for which the potential energy is 0. A natural choice is to take theta naught is equal to pi by 2. Okay, so we'll take at angle theta naught, that is when the dipole is with 90 degree, makes 90 degree with the electric field. At that instant, at that orientation, will take the potential energy of this system will be as 0. Okay, so why we are choosing this, it has been explained in the later part of this paragraph, but I'll explain it here. Okay, suppose we bring this dipole, okay, like this is electric field, and we are bringing the dipole like this in this orientation, perpendicular to the electric field. The dipole is perpendicular to the electric field. Then what is the work done on this charge? Okay, so you will say, suppose you will say, what is the work done on this? The force time distance. Suppose the distance move is, some distance is moved. Okay, suppose I'll say d distance is moved, and the force is what? The force on this is minus QE. Okay, and similarly to here, the force work done will be QE d. You see the work done in both cases are equal but opposite in sign. Okay, here positive work done is done with negative, because here I have to, external work has to be done. Okay, but here the electric field will itself do the work, because the negative charge will be attracted by the in this direction. Okay, so the total work will be 0. Suppose what if you take some values, so like 100 work is done on this, so minus 100 work is done on this charge, and 100 work on this charge, because the distance of both are equal, so the net work will be 0. And because the total work is 0, so I'll say that potential energy of the system in this orientation is 0, or there is no work done in bringing the unit positive charge, this dipole in this orientation. So potential of this dipole is 0 in this orientation, and this is the reason I have chosen 0 at that orientation. So now, so our theta naught we have taken pi by 2. Okay, and what will be the potential energy of dipole at another angle theta? It will have some potential energy. Okay, we have seen above. Okay, so that will be u theta. Just put the value of theta 1 as pi by 2, not pi, theta naught as pi by 2, and theta 1 is theta. Okay, so cos pi by 2 is 0. Okay, so what we'll get minus p cos theta, and we can write this in vector form. Okay, so this is p vector dot p dot e vector. Okay, this is the potential energy that is stored in the dipole at this particular angle, theta angle. Okay, it is better to write this in this form, p minus p cos theta. It depends on the angle orientation. Okay, at what angle it is placed. Okay, so now we'll see further. This expression can alternatively understood also from equation 2.29, and we'll try to explain it from the discussion we had in the previous video. We apply equation 2.29 the present system of two charges. The potential energy expression then reads. Okay, so if you remember in the previous video, we discussed the potential energy of two charges in electric field. System of two charges electric field is this. Okay, and now our two charges are our first charge is, we are taking the first charge as positive and second charge as negative. Okay, the charges of the dipole. Okay, so this will become, if you see here, yeah, so this is q, this is a positive charge, first charge. Vr1 is position, is potential. Okay, it's potential energy. This is what discussed in the previous video. Okay, this is the work done on bringing the charge in the at that point on electric field. Okay, so you can get the expression from there, minus, because the potential, the charge for second charge, that will be minus. Okay, and similarly this is what you get when you put the value of q and minus q there. Okay, now here r1 and r2 denote the position vector of plus q and minus q. Okay, so these are the position vector of the two charges of the dipole. Note the potential difference between position r1 and r2 equal to work done in bringing a unit positive against electric field from r2 to r1. Okay, so this is the what is this is this potential energy difference. Okay, vr1 minus vr2. So this is the work done. This potential difference is the work done in bringing the charge from r2 to r1. Okay, r2 to r1 against the electric field. So these are the position of r2 and r1. So against the electric field, what will be the work done? It will be equal to this potential difference. Okay, this is what we discussed in our previous chapter. Okay, or in our previous video, sorry. Okay, so this is the work done in moving the charge against the electric field from r2 position to r1 position. Okay, and now we know what is work done. Distance parallel to the force is 2a cos theta. Okay, so the electric field is in this direction and we are moving the unit positive charge in from r2 to r1. Suppose r1 is there and r2 is there, so we are moving it from r2 to r1 against the electric field. And now this is making suppose theta angle. Okay, so what will be the distance displacement along the direction of the force? This will be, okay, this will be what, 2a cos theta, because the distance between the two dipole is 2a, so this length will be 2a cos theta. So the displacement parallel to the force is 2a cos theta. Okay, so now thus vr1 minus vr2 is, this is the work done, okay, from moving charge from r2 to r1. This will be E times 2a cos theta, because we are applying the force in the opposite direction of electric field. Okay, so this is unit positive, we talking about unit positive charge, so this will be work done is what, force times the displacement. Okay, and this is q is 1 because we are talking about unit positive charge. So this is a work done in moving the charge from q2 to r1 to r2 to r1. Now when you put the 2a times q, this q will also be there, q into 2a is p. Okay, so this will be minus p cos theta, and this factor is also there, so it becomes minus p dot e. Okay, p dot e minus q square 4 pi epsilon naught times 2a from this here. Okay, so this is the potential energy of the dipole. We note that u dash theta differs from u theta by a quantity which is just a constant for a given dipole. Okay, if you compare 2.32 with 2.34, these two equation, you see the only difference between them is this quantity. And for potential energy, a constant is insignificant because it will be added to both of the orientation. Okay, it is like when I am finding the potential energy of 2 points like u1 and u2. Okay, so the potential of this is 10 and this is 20. Okay, so if I add constant on both terms, like 10 is added to both, when I find the potential difference, okay, so what I'll get, I'll still get 10, 20 minus 10 is 10. If I haven't added the constant, still I'll get 10 as the potential difference. So it doesn't matter if we add a constant term in the formula of potential energy, it doesn't have a significance. Okay, so that is why this can be reduced to that equation. Okay, so the potential energy of a system of a dipole in an electric field at a particular angle is what we can write, P minus P cos theta. Okay, so this is what you have to remember. Now we can now understand why we took theta naught is equal to pi by 2. Okay, this is what I already explained you. In this case, the work done against the external field is in bringing plus q and minus q are equal and opposite and cancel out. Okay, so I have already explained you this. Okay, and one more thing, so we can look at the potential energy of the dipole and different orientation. Okay, so if the theta is what, theta is 0 degree, so we can say the potential energy of the dipole is what, you will be putting in the general formula at theta is equal to 0, the potential energy of the dipole will be cos 0 is 1 minus p. Okay, and if theta is 180 degree, that is anti-parallel to the electric field, then in that case you will be what, minus plus p. Okay, cos 180 is plus minus 1. Okay, so this is the least energy that a dipole can have in electric field, so this is the most stable case. Okay, that is why we called it stable equilibrium in the case of when we find the torque. Okay, we said this is the equilibrium position, stable equilibrium, and this has the maximum potential energy when the dipole and electric field are opposite to each other, and we'll say that this is the case of unstable equilibrium. Okay, so this you have to remember. In the case of 90°, that is the potential energy is, in that case, is 0. Okay, so I hope I was able to make you understand this paragraph. Okay, this is a very important paragraph. Okay, so in our next video we'll talk about electrostatics of conductor. Okay, if you like this video, understand, you are able to understand from this video, please give like this video and subscribe to my channel. Press the bell icon for the notification of the next video. I try to make English as well as Hindi video simultaneously. Okay, so thank you.